Now, let us discuss existence and uniqueness of solutions of general ordinary differential equations, not necessarily a linear one. Well, so when you start thinking about it, the first thing that comes to your mind is probably the so-called Euler's method. And so let me try to explain what it is. So what is Euler's method? And so if we look at the direction field of the differential equation, and suppose that we want to construct a solution of a certain initial value problem, right? So suppose that here the initial value of t is -2. So -2 initial value of t, and initial value of y is 0. Right? So we can look at the vector in the direction field at this point. So what it tells us is that it shows us the direction in which the solution is going to grow or to decrease. Right? So it's going to tell us how the solution is going to change. So if initially it is at this point, so then it means that, well, the solution curve is going to move in this direction. So let's do the following thing. So let's just move in this direction by 1 unit in t. So we are going to take 1 unit in t, and then we're going to move in this direction, and then we get the next point. So then we're going to see at the vector from the direction field at this point. So it shows the direction, and then we're going to move in this direction so that the step is exactly 1 unit in t, and then we arrive to this point, and then to this point, and then to this point. This is if we try 4 steps. But then we can do the same thing with 8 steps. So again, we'll look at this point, and we'll move in the direction of the corresponding vector and we will move so that the distance in t is 1/2. But then we can try 16 steps or even more steps. And then the more steps we do, the kind of more like a smooth curve the result looks like. And then the way it is constructed is, of course, so that at each point of this smooth curve, the tangent vector here is going to be exactly the vector from the direction field. So, and of course you can imagine that if you take the limit of this process, then the limit is probably going to converge to the actual solution, right? So, and this is called Euler's method. So Euler's method is the following. So is a method of consecutive approximations to the actual solution, and each approximation is a broken line, is a piecewise linear function. And if we take the limit as the number of steps approaches infinity, then this limit is the solution of the initial value problem. But of course the limit is unique, so we expect that the solution of the initial value problem is unique. And the same thing is going to work for systems of equations too. Only if we have a system of equations, then this limit of broken lines is going to be constructed in a multidimensional space, but nothing serious is going to be changed about it. However, the situation is slightly more complicated than it looks at the first glance. So what is possible is that when you construct the successive approximation, then you can get something like this. So the first approximation looks like this, the second approximation looks like this, the third approximation looks like this, and so on. So which means that the end point of these approximations, it goes to infinity, right? And controlling for this is technically quite tricky, right? So it is true that there is always a unique solution, and it is true that Euler's method converges to that unique solution, but the domain of that unique solution, it may be smaller than kind of the domain of broken lines in Euler's method, and it's quite non-trivial to control it, right? So Euler's method is the simplest method to solve differential equations numerically, meaning compute the values of solutions approximately on the computer. And numerical methods is a big area of mathematics, so those of you who chose the applied track, you're going to learn more about numerical methods, but it's just for your information that there are many of them, and Euler's is just the simplest one, but it is actually big.